Alright, we're going to find the wee smallest tree. Minimum height trees. A tree is a blah 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 blah. It's explaining what a tree is. This is not my accent. Why am I talking like that? It's explaining what a tree is, and then they say, okay, return the list of all minimum height tree root labels, and you can turn the list can be in any order. All right, let's talk about what a minimum height tree is, because this is like a snoozer of a paragraph. All right. So take this example. Example one. This is the same tree written three different ways. And this will make more sense if you think of it from a breadth first search perspective. Now, breadth first search is actually not like a dissension. It's not like starting from the top and going to the bottom like you like typically picture. It's actually a rippling outward. You pick any particular starting point and you ripple outward to each next frontier. Rippling is a very good metaphor for this. So, in the example, if you were to start at node 0 and then ripple out from there, well, then you hit this level down here where you got one node in it. That's your first frontier. And then your second frontier is got these two nodes in it because these are the children of that. And that gives you a depth of 2. But if you were to pick your starting point as node 1, well, it has children. An important distinction, these are all undirected graphs. Excuse me. This problem is all, it's using undirected graphs. Yeah, undirected right there. That's where it says undirected edges. If you start at 1, well, it has children to all the other nodes. So the next frontier is this entire outer perimeter here. And so you have a depth of 1. And then what you see is if you start at nodes 2 or 3, it's very similar to if you started at 0, where it's going to have a depth of 2. So, starting at 2, go to 1, and then 0 and 3 are the children down, or starting at 3, go to 1, and then 2 and 0 are the next children out. So that's your example there. And then here's, I think, a more interesting... they're both very good examples on this problem. Sometimes they're kind of junk examples on these kinds of LeetCode problems, but I think these ones are actually chosen very nicely. So here we have a solution of 2 items, 3 and 4. These are our roots that we want to eventually return. So why are they the case? This is again the same graph written 2 different ways, starting each of the solutions. But how do you know which one to choose? Here's where I'm going to start talking about what the algorithm actually is. It's a little bit of a backwards breadth first search. So if you think about breadth first search as starting at a center point and rippling outward, well, what if we started at the outside and rippled inward to the center? Well, as long as we know when we've hit the center, that's our stopping point, and that's going to be our solution. So like by the time we hit a center, anything we've still got in that like center ring, we know there is our solution. So how do we know when we've hit the center if we're starting from the outside in? Well, first, one key is to how do you even identify what the perimeter, the outside is? Well, those are leaves. This is a tree where, there's no loops or anything. It is a proper tree. I'm not going to explain what a tree is here, I guess. You identify the leaves. Well, a leaf is something with one single child, since it's undirected. Or if it were directed, it'd be something with no children and only like a parent. But since it's undirected, a single child, or I guess a single parent is the same. Anyway, so you got 0, 1, and 2, and 5. These are our leaves. 0, 1, 2, and 5. And we know they're leaves because they have a connection to only one other node. All right, so that's our outer ring. Now we can remove that ring from consideration and take a step inward. So from 0, 1, and 2, our inner ring from there would be 3, and from 5 we move to 4. So from this, we go to 3 and a 4. Well, how do we know when we're done? Well, each of those has only one child that's not in like the ring we just came from, and it's each other. 3 and 4's only children are each other. So in that case, like the remaining quote unquote nodes are equal to the number of like leaves that we have. And so, if you were to say like remove these first leaves from the graph, you prune the leaves. I'm not just making that up. That is a common term. Then 3 and 4 will both be leaves because they would have only one single child. And that means we have only leaves left. So the number of nodes left, there's 2 of them. They're all leaves. It's the same as our number of leaves. So that's our stopping criteria. All right, let's start trying to do that in code. First trick is, how do you identify the number of leaves? If we write out, so we're given the graph in as a list of edges, and that's a fine way to represent a graph, but that doesn't help us count the leaves. What I'm going to do is rewrite the graph and in adjacency list format. Actually, let me take a step back and talk about target runtime and space complexity. Our target runtime, what are we estimating that we think we're going to be able to do? Well, breadth first search is linear time, and this is a tree, so the number of edges and nodes are about equal, so it's a linear time on the number of nodes. I'm just going to say O of n. I'm not going to say like n plus m, or it's not like the linear on edges plus nodes. It's just nodes, because that's really the same, and you got that constant factor. It washes out. So we're looking for linear time because this is pretty much a reverse breadth first search. We're going to have to like rely on some hashing tricks to actually make that true. And then hashing always comes with caveats. So we're going to have a hash set for sure. That is required in order to not get another linear factor multiplied in there. So actually first, so adjacency list format, that means we're going to have a list of nodes, and for each node, it's a key, like a map, like it's a map. So like 0, and its neighbors are maybe 5, 4, and 7, or whatever. That's listed twice, so let's remove that. And then like node 1, it's going to have neighbors of these, whatever. So, and then so on and so forth. So you list out for each node what are its children. So in adjacency list format, I'm going to use, you could use a vector of unordered sets, or you could use an unordered map of unordered sets. It depends on how, check with your interviewer on how like suspicious they are of like hashing. Because if you use an unordered map, which I'm going to use, you're still like playing with hashing again, which is like, you could say it's constant runtime, but there's caveats. And if you've taken an algorithms class, you'll be fully aware of what these caveats are. But in the real world, for all practical purposes, except in like the extremely rare edge case where you actually hit hash collisions, it's very, very fast. So include unordered map and unordered set. All right, so first we are going to, okay. And since we have to rewrite the graph, that's going to give us linear space on top of this input. And realistically, that's fine because we have to keep track of the leaves as well. And that's going to be linear space. And that's really the more crux one. So like once we already got linear space, well, we might as well use another linear space item because, well, what's the difference of doing it again? It doesn't, it just adds in another constant factor. So, so build adjacency list O of n time and space. All right, so unordered map of integer keys and sets as the values. Sets of integers. G for graph. 4. I'm just going to use auto here because it's going to get some like pair, and it's got some it's a nasty data type to write out. I don't know if your interview cares. You could ask him or her or them, ask your interviewer if they care about using auto or not for this, just something to talk about. So for auto, I'm just going to use K, it's just some temporary variable for k in edges. G of what are we doing? G of k dot first dot insert, because we're using sets. K dot second. And it's undirected, so that means we're basically adding two directed edges at the same time in both directions. That's realistically how you implement undirected graphs in adjacency lists, is you just have two edges, one going one way, one going the other. So G of k dot, what am I saying? Oh wait, this is a, I'm sorry. I was messing, this auto is not necessary because it's going to be a vector. So that's actually pretty simple. So I can change that vector of integers. It's really, there's always two items, and I'm gonna call it E for edge. So G of, I was getting ahead of myself. E of 0, G is E of 1, and then G of E of 1, insert E of 0. Getting ahead of myself with the notation there. Yeah, okay. What I was thinking of is the part where we need to now identify the leaves. Leaves, leafs, leaf, F, Z, I don't know. And then that's again O of n time and space. And this is fine to leave as a vector, it doesn't matter. All right, so this is what I was thinking of, where it's going to be some nasty data type auto k, and then it's going to be looping through the graph itself. Leaves dot push back, and it's okay. This is the adjacency list. So our leaves are the members of this. So these key values, if the length of its neighbors is 1. So if it has a single neighbor, it's a leaf. If 1 is the size, so G dot second, I guess. So since the way this is the first value, it's a map. So when you loop through it, this auto, this k thing resolves to, it becomes a pair. The first, so k dot first is the key, k dot second is the value, and the value is the unordered set. The key is an integer. So if 1 is second, k dot second dot size, then we add this to our list of leaves. So leaves, push back, k dot first. And that's our leaves identified. So then we need to do the main, now we're doing the main work. What's our stopping criteria? Our stopping criteria is gonna have to be, I gotta think about that. It's something and something. So stopping criteria, first of all, we're gonna be removing stuff. So just for the sake of like safety, I'm gonna put like a edge case check, or just like an error check. It's like guardrails for myself. There's probably a cleaner way to do it, but I'm gonna check if there are no neighbors, which there should be neighbors in the initial graph that we just created, but I'm gonna be removing them as we go. So if 0, or if oh right, so 4. Okay, actually, I'm getting ahead of myself. What do we do in this main loop? We're gonna be rippling inwards from the outside, and then we need to keep track of what the next inner frontier is gonna be. Well, leaves right now, this is our outer frontier. And in order to not kind of mess myself up, I'm gonna make another vector and like build that as the next frontier and then swap it. So vector int new leaves. And also, okay, yeah, okay, let's keep going. For what? For int L, I'm gonna do L, just so I not get, L is easy to get confused with one, so I'm doing two L's. For L in leaves, actually no, what I'm gonna call it I, and here's why. I'm gonna do this IJ notation for corresponding to, okay, what is J? Well, J is the other side of a particular edge. So we start with the leaf. We know it only has one edge. What's on the other side of that edge? So that is gonna be G of I dot, well, it's only got the one, but we're using sets. So the only way to access sets is through iteration. You can't access them with indices like you can with the vector. And the reason we're not doing vectors is because I'm going to be removing things as we go. And in order to do that in constant time, it needs to be an unordered set. Otherwise, we're going to have that linear factor multiplied in there. So G begin, and then that returns an iterator. So we want the contents of that iterator. And then, like I said, safety. So if G of what? If G of I, so if this particular leaf is empty, then we're going to continue. Just like I could remove it from the set too, but it's also like, we're only going to encounter it once. Why? Like maybe it would be a little cleaner for memory, but it's also like that's a little more work that we need to do. It doesn't really change much. And then the whole thing's going to get cleaned up when this function, like this entire function, finishes it anyway. So I'm going to leave it. I'm going to leave it be. So if there are no children, we continue because we removed them somehow and did something else. All right, so then we get our leaf. So like say we're starting at 0. Well, its child, it's only got the 1, so that's gonna be 3. The J is gonna be 3. So then we're gonna remove the edge. We're gonna remove the edges between 0 and 3. So G dot I dot erase J. That removes an edge, and they're going to remove the other edge. This doesn't remove any nodes, because remember the nodes are the key values in our map. So these are the nodes, and then these are like edges out. This isn't like a complete example, but it's adjacency list, meaning this is the list of edges going out from this node here. So that's fine. Erase I. And then finally, okay, so we've got our next item in from there. All right, what are we doing? The list of leaves. Okay, suppose would the leaves be? I'm thinking about deduplication. So suppose we're starting from here. Okay, well we get 3 as our next frontier in, and then that's gonna. Oh no, I take it back. So that's gonna have multiple things left. So in this, okay, starting from 0, we're gonna check 3, and then okay, so we're gonna count the number of edges out of 3. It's gonna still be like 3 of them. So we're not gonna add that to the leaves. We're not gonna add that to our list of leaves until we prune 2. And at 2, we remove 2, and then we say that, oh, 3 only has 1 edge remaining, and it goes out to 4, so 3 must be a leaf. And that counts on, okay, so since we're looping through the leaves and like not necessarily a particular order, not really guaranteed. So maybe we start at, would we be at 4? No, we wouldn't be starting at 4 because that's not a leaf. We're only looking at 0, 1, 2, and 5. So this edge is not going to get, there's no way that can get removed on the first pass. Okay, that's fine. So if 1 equals g of, I guess it would be I, so we're looking at leaf number I, and we got this number j, so j dot size. So if the new child on our other side, so yeah. So if 3 is a leaf, then we'd add it to our list of leaves, but it's not a leaf until that's gone. All right, so yep, leaves. New leaves, push back. No need for duplication. Push back j. And then lastly, we swap in the new leaves. And then let me add a return statement. Oh, return leaves. All right. Do I need anything else? I don't think so. It might be time to do an example. And then, okay, this is O(n) time, but not an additional O(n) space. So it's like breadth first search inwards, ripple, prune inwards. Need a stopping criteria. So I was saying it's when all of our remaining nodes are leaves. But how do we know when all the remaining nodes are leaves? Okay, realistically, you know what? Now that I think about this, we start out as a single tree. So is it possible for there to be more than 2 solutions? Like, is the list ever going to be more than 2 long? I don't think so, because the only way for that to occur would be as if it was like a graph and not just a tree where there's like multiple ways to go to things. But if it's a tree, then there's always going to be like either 1 at the center or 2 at the center. It depends on, okay, so this first example, we've got 4 total. Meaning, well, okay, it's not going to be total. It's going to be, yeah, I think there's always going to be 1 or 2, and that's it. There's not going to be 3 roots. So let's talk about depth. The minimum depth here is 1. That's an odd number, meaning we've got a single root. And here, the minimum depth is 2. Yeah, so 3 has got you go, if 3 is your root, you go 4 and then 5, that's a depth of 2. If 4 is your root, you go 3 and then one of these, 0, 1, or 2. That's, so based on the minimum, if the minimum depth is even, you're going to have 2 roots. If the minimum depth is odd, you're going to have 1 root, and that's it. There's no other possibilities. So our stopping criteria is while n is, let's say, greater than 2, and then we're going to subtract n. n minus equals the number of leaves. Yeah. Okay. I think I'm gonna do the example now. Okay. I'm gonna step through this leaves thing first. All right. So we start with 1, 2, 3, 4, 5. There's six in total. 6 for first round. We subtract off 3, 4. So that leaves us 2, and then that's it. Yeah, I think that's good. Let's do the example proper. This has been going on a while. Okay. I'm gonna do this second one, and then call that good. So here's our solution. We're expecting those. Okay. Taking our input. We get this as our input, and I'm gonna say, oh, I'm just gonna step through building this and not write. Oh, no. I take it back. Going back and forth. Let's do it properly. So in is that, and then so we build our graph. So for each item in this graph, we're adding 2 edges. We're gonna add 3, and that's gonna have an edge to 0. We're gonna have 0, and that's gonna have an edge to 3. And then, okay, edge number 2, 3, and then 1. So that's already got one. So we're going to add that. And then 1, we're going to add an edge 3. And then it's here, 3 and 2. Let's add another edge there, from going to from 3 out to 2. And then we add in node 2. That's got an edge to 3. And then 3 and 4, 4, 4, 4, 4. 4 going to 3. 5 and 4. Edge, oh wait, yep, getting ahead of myself. So 4 going out to 5, and then 5 going back to 4. This is our graph in adjacency list format. Okay, so I can safely scroll past this because we're not going to hit that again. Identify the leaves in O of n time. So 4, we're looping through this. So our leaves, what was that? Or if the length is 1, we're going to append it, push back k first. All right, so 3, that is a long length, so no, that's not a leaf. 0 is a leaf, 1 is a leaf, 2 is a leaf, and 5 is a leaf. Is that what we match on the picture? 0, 1, 2, and 5. Yep, that's what we expected. Okay, so we identified the leaves. And now we've got, so while n, we've got to keep track of n. N is starting out as 6. I'm going to put that up, write that up here. N is 6. So our length of leaves, okay, so while n is greater than 2, it is 6, so that's fine. Then we're going to subtract off 4. So we've only got, I guess, the 1 iteration. Okay, well, that's fine. So n now goes to 2. We've got new leaves. Let's write that out. New leaves. Add some tabs for alignment. New leaves for each I in leaves. So let's say we are, I guess I'm going to go ahead and erase as we go because we're not removing items from leaves, but just for the sake of illustration, I'm going to remove things as we go. For I in leaves, if it's empty, continue. Okay, so starting off with 0. If, all right, so we're going to get j. J is, so we're going to start off with 0. So that's this. So j is 3. J is 3. So we're going to remove the edge between 3 and 0. So 0 and then that. Those are gone. And then if, so j is still 0, the size is, oh wait, j is, wait, I is, I'm sorry, I'm going to write this out. I is 0, j is 3. So if number 3, so number 3 has one neighbor, we're going to add it to the loop, to the list. We are not. That is not a leaf. And that's what I mentioned before. It's still got these neighbors 1, 2, and 4. So it is not a leaf. All right, next loop iteration. looking at 1. So I is now 1, and then j is still again 3. All right, we're going to remove the edge between those two. So 1, 3, 1, and 1, 3. That's gone. And then so j is still 3. That is still like more than one neighbor, so that's not a leaf. Continue. Now we're looking at 2. So 2, we've got 2. It has an edge to 3. So we're going to remove the edge between 2 and 3. So remove that. Remove that. And so we're removing the edge between 2 and 3. Now we're looking at 3. Well, 3 has one edge remaining. We've removed those 3 leaves, and there's this one edge to 4 remaining. So that is a leaf. We are going to add that to our leaves. Okay. And next leaf is 5. So now our I is 5. And then 5 has one connection, so that's going to go to 4, between 5 and 4. Well, we're going to remove that, obviously. So 5 to 4. And then 5 and 4, we're removing that bidirectional edge. J is 4. Well, node 4 has one child. And so that means 4 is also a leaf. We're going to add that to new leaves. Do we do anything else? I think that's it. Oh, look, I think, yeah, I didn't remove that. So we're done with our list, our original list of leaves. So now we swap it. So now leaves becomes 3 and 4. And then this gets washed away when the loop ends because it's declared inside the loop. N is now 2, so we're not going to do another iteration. We're going to break out the loop, and then we're going to return 3 and a 4. And that is our expected solution. Okay, this was a long one. Let's give it a run for syntax. You know, these are always long ones. I need to really cut down my time. What? Unordered map. Unordered map. File not found. Unordered. What? Not found. That is definitely a header. Well, let's see if it's already included anyway and just go from there. Okay, so LeetCode includes that by default. It is I'm like 99.9999999% confident that it's unordered map is the correct header to include if it's not already included in your testing environment. But that seems to do it for our regular run. I'm going to submit and fingers crossed, come on, no. Oh, okay. Edge case. All right, so you see these constraints here. If there's a single node, it's not going to have any edges. And I didn't check for that, I guess. So, okay. If there are no edges and there's a single node, so I guess, so n is always at least 1, so n's always 1, edges are always n minus 1. So if n is 1 or if edges is 0, if 1 equals n, return, and we want to return a vector. So you can do this braces and just put a 0 and it'll resolve to a vector on the return. Okay. All right, yeah, I didn't think about edge cases. My bad. That is a ding. That's something to think about in interviews. You do want to check for edge cases. And for good measure, I will write that out. Yep. Okay, please, please, please. Don't fail me now. There we go. Boom. All right. Sweet. Let's go ahead and mark it off. Minimum height trees, and good night.